thank you very much for coming. My name is Kalen Delaney. I've been working with SQL Server for a very long time, and we're going to talk about something that's been in the product for quite a while. It isn't one of the brand new features. It isn't one of the newest technologies that you maybe never have heard of before. It's something you've probably heard of, but maybe you don't understand exactly why it's so powerful. I'm going to be talking about partitioning of SQL Server tables and indexes, and actually what is it about partitioning that makes it such a powerful feature. This isn't so much a best practices. It's not a development talk about how to actually implement partitioning in your code, in your applications. It's how partitioning works behind the scenes so you can understand exactly when and where it might be useful to you. So, as I mentioned, I've been using SQL Server for quite a while now. It's over 31 years since I started working with the Sybase Corporation, which is where SQL Server was born. I've been working, when I work with SQL Server. I do have a life. I've got a dog. I've got kids. I even have a grandson in Germany. My little grandson lives just a couple of hours south of here in Stuttgart, and I will be seeing him tomorrow. So I have other things in my life besides SQL Server, but when I'm working, it is SQL Server. I write about SQL Server. I teach about SQL Server. I do troubleshooting and consulting. You can contact me. I've got LinkedIn. Twitter's probably the best way right now. And I do have a public Facebook page just called SQL Internals. So I won't read the whole description here. This is what I submitted to the conference, but basically we're going to look at why partitioning is such a cool feature. It's not new, it's been around, but if you are still not sure about exactly how it does what it does, that's what you'll find out here. But to understand why partitioning is such a really cool feature within the product, we have to understand how SQL Server stores your data. And to understand how your data is stored, we need to take a look at the metadata, the data about the data. So we'll have a little overview of the metadata, particularly the storage metadata. Then we'll start talking about what partitioning is for, what are the use cases, what are the benefits. The real magic, that's the title of this presentation, the magic of partitioning comes in when we do an operation called partition switching. So once we understand the metadata, I'll be able to show you behind the scenes exactly what happens when you do a partition switch, and you'll see why it's magic. It's possible to redefine your partitions if you've got a partitioning system that needs to evolve over time. I'll show you what's involved with that. And it involves two operations called split and merge, but there are some caveats, there are some warnings I have to give you about split and merge. They're not quite as magic as switching unless you're really careful. So, how many of you have used SQL Server since before 2005, since before version 2005? Okay, looks like almost half of you, maybe a little more than half of you. I do find that when I speak to European audiences, it does seem that there's a whole lot more people who go back a lot further. Sometimes with American audiences, it might just be a few people have gone back to 2000 or 7, and rarely anybody who goes back further than that. So we've got a lot of old-timers, a lot of people who used the product before all the metadata was completely redefined. In SQL 2005, I call what happened the Metadata Revolution, and Microsoft completely redesigned how we get information about our data, about our objects. One of the changes is you no longer can directly access the system tables unless you're using this interface called the Dedicated Administrator Connection, We're not going to be talking about that today, but it is a way to get to the system tables directly. Otherwise, we use a set of views, and there's two flavors of views. We have compatibility views, which have the same names as the old system tables. One of my examples will show you one of the old system table compatibility views, but the recommended interface is a set of catalog views which look a little bit different. Their intention is that they'll be easier to use, they'll be completely documented, there'll be no more hidden or secret columns, no more bit strings that you have to fiddle with and do bit arithmetic, which is always one of my favorite things to do. It made me feel real geeky and really cool, and the new kids never knew how to do it. So when I did the bit arithmetic, it just made me feel real special. So I didn't like it that they got rid of all the bit fields, but sometimes it does make things easier. We're going to focus on the storage metadata, the metadata that keeps track of your tables and of course, your indexes as well. So we'll look at the physical object storage, we'll look at something called allocation units, and then there are three main views we'll be looking at that we'll need to understand to start talking about partitioning. Anytime you create a table in SQL Server, there's only two different ways that table can be stored. The table can be stored as a heap, which is basically just a bunch of rows on a bunch of pages with no ordering. A heap is an unorganized set of rows. There's no first row, second row, or last row. It's just a bunch of rows. If you want ordering with your data, you need to create an index, and indexes in SQL Server are stored as B trees. We're not going to be able to go into the details of B trees, but it's the alternative storage to a heap. Every table is either stored as a heap, or if you create a clustered index on it, the entire table is then stored as a B tree. So when you create either a table or an index, you need to tell SQL Server where to store that table or index. And there are two places the table or index can be stored. You can say, create this table on a file group, or you can say, create the table on a partition scheme. And we're going to be looking at exactly what a partition scheme is. Of course, I'm sure you've all created tables where you didn't say either one. You didn't say create the table on something. So of course, there is a default. Anybody know what the default is? Somebody said the primary file group, which is close to the right answer. It's actually stored on the default file group, which by default is the primary file group, but you can change what the default file group is. So it might not always be the primary file group. If you want your table stored on a partition scheme, that has to be explicitly stated when you create the object. So the syntax, create table or index on file group or partition scheme. We'll see examples of this with partition schemes. The data itself has three different formats for being stored. There's three different types of pages for storing your data. Your regular rows of data are stored on what we call regular pages. You can also, as of SQL Server 2005, have something called row overflow data where you have variable length columns, varchar, that just doesn't fit on the page. As of SQL 2000, you can create a table with 10 varchar 8,000 columns and fill them all up. They wouldn't all be stored on a single page because pages are only 8K. The data that doesn't fit on the page is stored on special pages called row overflow pages. And then the third type of page for your data is a large object or a lob page. Lob pages can store a whole lot of, well, the page can only store 8K. All pages are 8K, but a column with lob data can be up to 2 gigabytes in size. So the data is stored in its special way in its own tree structure to help SQL Server organize it. So another way of viewing your data storage is that we have a table. It actually might be an index as well. That top object could be either a table or an index. The table or index can be split into multiple partitions. Each partition is either a heap or a B tree, and then the heap or a B tree is composed of 3 types of pages: regular data, large object, and row overflow. You might not have any large object or row overflow for certain tables, but every partition of every table could have all 3 of those types of storage. A few more basic terms before we start actually looking at the metadata. Pages I just mentioned are always 8K. That's the minimum unit of I/O. Reading is done at least a page at a time, maybe more. It might be read an extent at a time, which is 8 contiguous pages. But SQL Server never reads just a row at a time. Extents are 8 contiguous pages. That can be a unit of I/O. It's also the unit of growth for a table. When a table gets filled and it needs more space, it gets another 8 pages, and then another 8 pages. It doesn't get 1 page at a time. It grows by 8 pages at a time. You can take a table and split it into chunks called partitions, and that's what we're going to be looking at in the session here. We'll start in just a minute looking at the details. A partition table is one that is split into pieces. When partitioning was first introduced, the upper limit was 1,000 partitions. In SQL 2008 R2, Microsoft increased that limit. You can now have 15,000 partitions for a single table or index. Each partition, as we saw in this picture, can be made up of 3 different kinds of pages. All of the pages of one of these types, and here's where I need my magic pointer, data, the regular data, lob, row overflow, all of the regular data for one partition is called an allocation unit. All of the lob data for one partition is an allocation unit. All of the row overflow for one partition is an allocation unit. So all of the space for one partition for one of those types of storage is an allocation unit. And this we need to have some understanding of as we start looking at the catalog views. That what I call the big 3 catalog views are listed here. We have sys.indexes to replace a previous table called sysindexes without the dot. Sys.partitions doesn't replace anything because we never had partitions before. And sys.allocation units. We have to combine all 3 of these to get the whole picture. There is a undocumented companion view to sys.allocation units with a really cool name, System Internals Allocation Units, which looks just like sysallocation units, except it has 3 very special columns in it, and we'll see those in a minute when we have our first demo and look at the metadata. So sys.indexes has 1 row for every table and 1 row for every index. If the table has a clustered index, there will be a row with an index ID of 1. If the table is a heap, there will be a row with an index ID of 0. And then there can be other rows for all of the other indexes. You'll never have both a 0 and a 1 for the same table, but you might have a 1 and a 2 and a 3, or a 0 and a 2 and a 3 for the same table. There's a column called indexes.type, sys.indexes.type, which has one of the values you see here. These are really all the different kinds of indexes SQL Server supports. We're not going to be talking about all of them. This is not a session about indexing, but there's some really cool things here. Maybe somebody else will have a session on that. And then we have a view called syspartitions, sys.partitions. Each table or index always has at least one row in sys.partitions. Even if you don't know anything about partitioning, every time you create a table, you get a row in sys.partitions. It's assumed a table is on a single partition unless you say otherwise. And so there's a join between sys.partitions and sys.indexes. It's a composite join on both object ID and index ID. We're going to see this in an example in just a minute. Partition ID is, you can think of as the unique identifier for each partition. It's actually the same as another column called Hobbit ID. And when we look at the metadata, I'll tell you a little bit more about why we have both of them. So object ID, index ID, and partition number is not the same as partition ID. Partition ID is this long 16-digit number that no one would ever even want to say, where partition number is just your counting number, 1, 2, 3, 4, up to 15,000, which you don't want to count to either. But your partition number is just your sequential number. Your partition ID is this long identifier. We'll see that in the metadata in just a minute. And then the third view, sys.allocation units, one row per format per partition or Hobbit. I didn't mention Hobbit here. I think I edited the slide. Remember, I should have added that in the list of terms that we've got. I said every table is stored either as a heap or a B tree. That's what Hobbit means, heap or B tree. And in fact, when this new storage metadata was first being introduced in 2005, I was working on a book for Microsoft, and I was spending time with some of the engineers, and I heard them talking about this concept before I ever heard it written down. I heard them talking about hobbits. And what are they talking about here? And then when I finally saw it written, I realized, oh, this must be an acronym for something. But I heard the word before I saw it written. I mentioned the three formats already. Sys allocation units joins with sys.partitions on a column called container ID. And I'll say a little bit more about that in just a minute when we look at the metadata. And we will look at system internals allocation units as well. So let's do it. Let's have our first example here. I'm going to be looking at SQL Server internal version number 14, which is also something that the true SQL Server geeks need to know. What real version is internal number 14. That actually corresponds to SQL Server 2017. And if you know that, you get 10 points. So let's look at the basic metadata here. I can build a brand new database called TestDB. Just so you know, it's nice and clean. Oops, and this won't go because this one's already in TestDB over there. Let's get it out. There we go. Brand new database. And I'm going to create a table with some very big rows that almost fill a page. A char 1000 and a varchar 7000, which could almost fill the page. I'll insert one row that isn't going to be the full page size, 1,000 bytes in the first column. I love this little replicate function to create sample data columns. If I want something really long, I don't have to do a lot of typing. Replicate A 1,000 times, replicate B 1,000 times. Hey, I've got some big wide columns here now. So what do I have in this table? Sys.indexes shows me one row for this table. It's a heap. I haven't built an index on it yet. Sys.partitions has one row with a partition number of 1. That's all there is 1. It has a partition number of this big, long string of digits. And notice, exactly the same number is in the column called Hobbit ID. Why do we have 2 columns with exactly the same value? Well, you might think maybe they're not always the same value, but I'll put it to you that if you go to every single database you have and you do a select from sys.partitions and say, give me all the rows where partition ID does not equal Hobbit ID, you'll never get any rows back. Partition ID is always equal to Hobbit ID, so why do we have both of them? Well, here's the answer. Originally, when 2005 was first being written, Microsoft planned that in the next version, 2008, Hobbit ID was going to mean something different. That was their plan, was that it was going to diverge a little bit, so they wouldn't always be the same. They changed their minds. But in 2005, when they introduced this new metadata to us, they also promised that all the new catalog views would always be forward compatible. They would not make any changes that could ever possibly break any of your scripts. So if you wrote a script with Hobbit ID and then they took it out, that wouldn't be very nice. And because they said that they guaranteed this, we're stuck with this duplicate column to this day. So there are still Microsoft-provided scripts out there that use Hobbit ID instead of Partition ID, so it's probably good they didn't get rid of it. We could just ignore it, or we could use it in place of Partition ID. They are always the same. And then we have allocation units. Because Hobbit ID and Partition ID originally were going to mean different things, in sys allocation units, we don't join with Partition ID or Hobbit ID. We join with a column which could mean either one. They came up with a new name, Container ID, which they thought sometimes would join to Hobbit ID and sometimes would join to Partition ID. But because they're always the same, it actually joins to either one. So, but they call it Container ID. So I can use Container ID to find the matching row in sys.partitions. And I only have regular in-row data. I haven't done anything special because I didn't use any of my special data types or fill multiple varchars that ended up giving me row overflow. But if I recreate this table with a text column, oops, no, I didn't run that, and run it, and then insert, including 10,000 bytes into the text column. I didn't really put 10,000 bytes in there. Data length tells me it's only 8,000, and that's because replicate assumes this C is a regular varchar, which has an upper length of 8,000. It quietly truncates anything after 8,000, and we're just left with, we can't get to the full 10,000. Unless we do something else I'll show you in a minute, but let me just show you this container ID here. Now I've got 2 allocation units, one for in-row data and one for lob data. I'm going to recreate the table a third time, this time with a varchar 8,000, so it's possible I could have rows that are too big to fit in an 8K page. If I fill the varchar with 8,000 and then have the char 1,000, that's too big to fit on a page. So now when I look at the details of this table, I do have an allocation unit for row overflow data. I don't have anything in it yet. I didn't put any data in I can do that with inserts, but we're gonna, oh, here's the trick I wanted to show you, how to get more than 8,000 characters with replicate. I need to convert that character string to a data type that does hold more than 8,000, and I can convert to a varchar max. Conversion doesn't work with text and image, but it does work to convert to varchar max. So if I convert a string of 10,000 Fs to varchar max, then I actually do have 10,000 characters, a length of 10,000 in this row here. And now when we look at sys allocation units, I see that there's 9 pages for the regular data, 9 pages for the lob data. Although I have an allocation unit for row overflow, there's nothing in it yet because I didn't overflow anything. I just made it 1,000 bytes and 1,000 bytes. But we're getting off topic here a little bit. I'm not going to go through the rest of the examples. It's more just playing around with the regular metadata. We need to start talking about partitioning. So partitioning is a way of taking a table. Usually it works best if it's a big table, and you divide it into chunks. Usually we divide it into chunks based on the value in a particular column that we call the partitioning key. One of the columns acts as the separator. Very, very frequently, partitioning is done based on a column that's a date-time column, so that all of the rows with a date between January 1st and February 1st go in one partition, between February 1st and March go in another, March 1st to April 1st go in another, where the first of every month would be the dividing point between the partitions. My example isn't going to do that. It's a little more involved to work with, but very frequently partition tables are separated based on the dates, and it allows you then to separate sales data or orders or anything that you're keeping track of in a calendar fashion. When you create a partition table, you specify a partition scheme instead of a file group. But what a partition scheme is, we'll see in just a minute, is a set of file groups. You basically give a list of file groups so each partition can go on its own separate file group. But partitioning is only visible when we start poking around the metadata the way I was just showing you. You can see that you have multiple partitions if you look at sys.partitions or sys.allocation units. You can't see partitioning if you just run queries. We'll talk about partition functions and schemes in a minute, but what I want to tell you is the big benefit of partitioning before we start creating one. Partitioning can have some benefit if you split a table in partitioning into partitions, and then you have another table that you split into partitions, and then you're joining them. If the partitions you're joining, or if the way that you join has one partition here, just join with one partition here, that can be a lot faster than joining to anything in the whole table. To narrow down, and one partition here joins with one partition in the second table, can make the join a little bit faster, but that's not really the biggest benefit of partitioning. The biggest benefit is data loading and unloading. So let's say you have a table of your sales history. You've got your last 12 months of sales history, so the oldest one is February 2018, and it goes all the way up to January 2019, last month. And at the end of this month, at the end of February this month, you want to take February's data and add it to the sales history table that you're keeping track of, the big table. Let's say you have 100 million rows in the big table. And then this month, in February, you get another 10 million sales. How expensive is it to insert those 10 million new sales rows into a 100 million row table? Very. Normally, it would be very expensive to do 10 million inserts into a table, especially if you have multiple indexes on the table. It's very expensive, unless or except if the table is partitioned. If the table is partitioned by month, you can take the table that has February data, and basically you just pick up that table and you hook it in to the big table. It's an instantaneous operation to pick up February's data and hook it in to the big table. And then, of course, we only want to keep 12 months of data, so we want to get rid of February 2018, or maybe move that to another location. I want to get rid of the 10 million rows from February 2018. Normally, deleting 10 million out of 100 million is an expensive operation. But if it's partitioned, all I do is take that one partition and I basically break it off like a bunch of grapes and put it on a separate plate somewhere. So it's no longer part of the big table. That's the magic of partitioning, and we'll see exactly how that happens. Loading in a whole bunch of data by just adding a partition into a table, or getting rid of a whole bunch of rows by just removing a partition. But before we can start doing that, we have to understand the prerequisites. You must figure out a column that's going to be used to separate your data into chunks. I mentioned it's frequently a date column, but it doesn't have to be. Basically, you create a partitioning function, which is just a bunch of data values, which become the boundaries of your partitions. Each row, then, is assigned to one of the partitions based on which boundary points it's between. After we define the partition function, I'll show you this dollar partition in just a minute. It doesn't make much sense if I just talk about it. Then we come up with a partition scheme, which is a list of file groups. All a partition scheme is a list of file groups. There has to be at least as many file groups as there are partitions. So if you have 4 boundary points, that gives you 5 partitions, everything less than the first one, everything between the first and the second, between the second and third, between the third and fourth, and then anything greater than the fourth, that would be 5 partitions. You have to have at least 5 file groups. It doesn't have to be 5 different file groups, thank goodness. But it has to be 5 file groups mentioned. So here's a couple of examples. Create partition function. I'm just calling it test function here, test fn, as, and it's a range separation, and I'm listing 4 values, -1, 10, 20, and 30. 4 values will give me 5 partitions. Everything less than -1, everything between -1 and 10, between 10 and 20, between 20 and 30, and greater than 30. Well, so of course I know the question you're all wondering is, what happens if I insert a row that's exactly equal to one of the boundary points? What would happen if the table that's going to have this partition function got a value of 10? Would that go in the second partition or the third partition? In general, the answer is it depends. Specifically, because I have a range left, that means the left or right, which is the alternative, basically just defines what happens to values equal to the endpoints. Range left means something equal to the endpoint goes with the values to the left, which are smaller. Range right would mean it goes to the values to the right. So a 10 would go with the values 0 through 9. A 20 would go with the values 11 through 19. And we'd have to be greater than 30 to go in the last partition. This $partition namespace, you can think of it, the $partition namespace allows me to call a partition function independently. You can do it just to verify that your boundary points are correct, that values are going to go into the partition you hope they go into. Now, we don't have a table yet. We don't have any data yet. Creating a partition function just creates some abstract values that are boundary points. We have to then create the partition scheme, which is at the bottom of the slide, and you can see it's just a list of file groups. These file groups must exist. If I have not created a file group for, I'll get an error with this create partition scheme command. I need to have at least as many listed, and I have 5, but they're not all unique. I have file group 1 listed twice, and I would never do what I have on this slide. This is just to show you it really doesn't matter, the fact that I listed the same file group twice, and I have this weird order, file group 4 at the beginning, file group 2 at the end. The order is important, however. It means the first partition, everything less than or equal to -1 will go in file group 4. The second partition, everything greater than -1, less than or equal to 10, will go in file group 1. Everything between 10 and 20 goes in also file group 1, but it's stored separately. The fourth partition goes in file group 3, and the fifth partition goes in file group 2. I was just trying to make it as confusing as possible. Just so you know it is possible. You don't have to do it that way. Once I have my partition function, setting up my boundary points, once I have my partition scheme, I then can create a table on that partition scheme. See at the very bottom of the slide, on my partition scheme, and then I mention the column in the table that determines which partition each row goes into. In this table, I have a column called EMP-ID, Employee ID, and it's the value of Employee ID that's going to determine where the row goes. So what columns can be the partitioning column? Almost any column. It has to be just a single column, however. I know over the years there's been hundreds and hundreds of requests to allow partitioning on combinations of columns like city and country, or first name and last name, or date and region. Hasn't happened yet. You can have a computed column. That could be a partitioning column if you really need 2 different values together to determine the partition. Almost any data type is possible with a very few exceptions. It can't be any of the extra large data types, the text or image, or the varchar max, or var binary max, of course. User-defined types, I think that's old news. I believe user-defined types are now allowed. And I'll need to go and check that. That was a recent change, so I'll need to double check that. So let's actually do it. So then we can start playing with it. So I have a second script here to just set up a very simple partition table. This is basically the one or very close to the one we saw on the slides. There's several tables that my examples are going to be using. I'll drop them all before I start. This is one of my favorite 2016 features. If you're not running 2016 yet, you can't do this. To drop if exists. It's so cool. Otherwise, you have to say, like I do for partition schemes and partition functions, which don't allow the drop if exists, I have to have 2 parts. If it exists, there is a table with this name, then I drop it. I have to do that with the partition scheme and the partition function. So here's my partition function. The 4 values create 5 partitions, -1, 10, 20, and 30. And this $partition allows me to specify a partitioning function and pop in any value. It doesn't have to be a value in a table because I don't have a table yet. I just have this function, but it would allow me to check my boundary conditions. You told me, ooh, that's fun. Can't be a power failure because I still have my screen. So I'll talk in the dark here. You told me that 10 should go in partition 2. Let's see if SQL Server agrees with you. And yes, it does. Here's the partition scheme. And there's a shortcut if I want all partitions to go on the same file group. I only have one file group, which is my primary file group. So all the partitions are going to go there, but they will be separate. We'll see that in a minute when we look at the metadata. Here's my table on this partition scheme. And then I'm going to just grab a bunch of data from another table in another database from my AdventureWorks database. I have a bunch of first names, 60 rows. I mentioned partitioning usually is a good idea when you've got huge tables. 60 is not huge. But for our metadata purposes, it's good enough. The $partition with the name of the partitioning function can actually be used in other queries. I can look now to see for every single value in the table what partition it's in. For all 60 rows, it will tell me. Some of the rows are in partition 1. Then I have rows in partition 2, 3, 4, and 5. For every row, $partition with the actual column will tell me what partition it's from. I can also use this $partition in a group by to see how many rows are in each partition. It's pretty evenly split with one exception. And you can use this for any partitioning function. Well, now we're back. So now let's look at the big storage query. This is going to do a join between all 3 of the, oh, I'm in Germany. I got to go that way, right? All 3 of the tables that I just talked about. sys.indexes, sys.partitions, and sys.allocation units are all joined together looking at the employees table. And I get 5 rows coming back because there are 5 partitions. So there's the partition number. There's the number of rows. There's the partition ID. There's the allocation unit ID, which is the same, the container ID is also the same as the partition ID. Number of pages, and I mentioned that this system internals allocation units has special columns in it. 2 of the special columns are the actual page numbers that the partition starts on. So the first page and the root, if there's an index, I don't have an index, so the roots are all 0, but I see the first page number. Being able to see that is important when we start moving things around. Building an index, oh, actually, let's go back there. Just try to remember some of this number. You know, there won't be a quiz, but its first page is hexadecimal, 9001, and then a bunch of zeros, and then 100. But once I build the index and look at the data again, the exact same query, you should know this, it's a completely different page. When you build a clustered index, all the data moves to all new pages. So the page numbers are going to be different after I built that index. So I've got a table now split into partitions. 5 partitions, always partitions are numbered consecutively. starting with 1 up to however many partitions you have. So now we're ready to talk about the magic. The magic is taking a whole partition and moving it as a unit somewhere else. It's an instantaneous operation because the only thing that gets updated is the metadata. Now, I described it as moving the partition to take a table and hook it into a partition table, or take a partition and move it to a standalone table, but that's not exactly what's happening. The operation is called switch. We actually have to have something we're switching it with. Data is moved, partitions are moved between tables by doing a switch. I've got a picture to show you, and then we'll have some examples, and all that gets updated is the object that the partition belongs to. No data moves. By looking at the page numbers, you'll be able to see that the data stays on the same pages. It just now belongs to a different table. The only thing that's updated is the object ID and possibly the partition number. So here's what it looks like. It's an alter table operation because we're actually changing the metadata for a table to give it a new partition or to remove a partition. Alter table, table 1 is called the source. Switch, and there's certain variations of it. We can either switch a partition of the table to another table, or we can switch the whole table to be a partition of another table. There are 3 different possibilities. Table 1 is the source. Table 2 is the destination. The destination, or the target, must be empty. You're switching something that has data into something that's empty. And there's 3 different ways partitioning can be done. We can take a full table, a populated table, and switch it with an empty partition. We can take a populated partition and switch it with an empty table, or we can switch a populated partition from one partition table to another partition table, as long as the target is empty. So actually, I'll come back to this slide. I wanted to show you this picture here. So instead of 12 months, because that wouldn't fit on the slide, let's assume we've just got a table partitioned by 4 quarters. Q1, Q2, Q3, and Q4 hasn't finished yet, so Q4 is empty. But as soon as Q4 is done, I've got a table where I've been collecting Q4 data, and I do my switch operation. I switch the source table 2 into partition 4 of table 1, and what was partition 4 of table 1 now is in table 2, which is basically nothing. Table 2 would be empty after this switch operation, and partition 4 would have all the data that was in table 2. So a few other things to think about. I did mention a couple of times the target has to be empty. The source and the target must be in the same file group. That's something that sometimes people forget or mess up on. If we want no data movement, they have to be on the same file group so the data can just sit where it is. There's a list of other requirements you can check in the documentation, but the most important second thing besides the same file group is that the index structures have to be the same. The source and the target basically have to have the same indexes defined for them. So they're very, very similar tables. Indexes can be partitioned almost the same way as tables, and we can have a table and its indexes partitioned the same way. We call that an aligned index. So let's look at it. Let's look at the actual operation of switching switching a partition from one table to another. Now, before we do that, I want to show you another demo, and I will be making all of these demos available. I forgot to open my Zoomer. Where is that? Nope, that's not, that's my on-screen keyboard. I thought I had a Zoomer here. Zoom it. All right, so all the demos that I'm showing you, I will be making available. There's a couple here that we're not going to have time to look at. Sometimes I do this as an hour-and-a-half presentation, not just 1 hour. But I have a special view that I use a lot that actually, this script goes through a lot of the metadata that we haven't looked at yet. But it also creates this very large view that involves all of the partition metadata. We won't be going through all the details here, but you will have access to this. It does require a function to return an index name, so that I've already created, or I also create in this script, a function called index name. I'm always amazed that that doesn't exist, but Microsoft hasn't created it and supplied us with index name function yet. Now I have this giant function called partition info. And very simply then, I can just say, give me all the partition info for a particular object. Is it like watching my movement? Is it like in the restrooms, you know, where if you're not moving around, the lights go off? If I stand up here and dance? Hey. No, apparently not. So when one simple little query selecting from the view shows me the 5 partitions and all of the details about each of the partitions, including the number of pages and what the boundary points are. So now let's look at the switch. After all that, we're ready for the big time, looking at switching happening. So I'm going to create a second table called employees 2 with exactly the same structure, the same clustered index on the emp ID column, and then this query will look at both employees and employees 2. And notice some things to make a note of here. Oh, come on. The regular employees table has 5 partitions that all have some rows. Employees 2 has 5 partitions, and all of the partitions are empty. But I'm going to switch the first partition here with the first partition here. So let's remember these partition numbers. This one ends in 2-8. This one ends in 8-8. Do I also have page numbers? I have page numbers here. Not like you have to remember them. This is all zeros. This starts with an E. And when I do the switch, the partition 1 from employees to partition 1 of employees 2, and then look at the metadata again, notice partition 1 here is empty, but it's partition number 80, and partition number 1 here is populated, and it's 20. It's the same partition number, it just belongs to a different, it's the same partition ID, it just belongs to a different table now. And it also has the same page numbers. It's the same data. It hasn't moved. It's just belonging to a different table now, and we can move it back. I can switch it back the other way. And now everything's back the way it started. All the rows are in the employees table, not employees 2. One more example, and that is a standalone table. I'm going to create a table called employees 3, but that is not going to be partitioned. That's just going to be a standalone table. So if I look at employees and employees 3, I see that employees 3 has a single partition that's empty. It ends with 104 is the partition ID. And I can switch the first partition of the big table into the new standalone table. And again, I see that now the first partition is empty, and employees 3 has the 10 rows. The first partition has partition ID that ends in 104. That was the original standalone table. But here's the gotcha. When I try to go back the other direction to switch from the standalone table into partition 1, I get an error. It's complaining about constraints. What constraints? I never built any constraints. Well, that's the problem. A partition function is sort of an implied constraint. Every partition is constrained to have values between the starting boundary and the end boundary. When I switch data from a partition into a standalone table, the standalone table can take anything. But now I'm trying to switch things back into partition 1, and partition 1 has some rules. Partition 1 has to be values that are less than -1. If I did a select from this table, well, if I do a, put my fingers, there we go. Select from employees 3, come on. I do see that all the values are less than or equal to -1, but SQL Server can't be sure when I try to do this switch that all the values actually meet the rules for partition 1. It will not allow me to do this switch until I actually add a constraint to the standalone table. The constraint that says all the values have to be less than or equal to -1 guarantees to SQL Server that all the rows will actually fit into partition 1. And now there's no error. Now all the data is back where it was. If you want to do more playing around, there's a script to move data in a table that has large object, that has a text column. You can see what happens as you try to move partitions with a table that has a text column. There's also a script for this last topic that I will just be talking about, and that's when you need to change your partitioning definition. There are 2 additional operations SQL Server supports called split and merge. These are done on a partition function, not on a table. We're not altering a table. We take the partition function and we add a new boundary point. So instead of having a boundary between 10 and 20, we can say add a new boundary point at 15. And that one partition will then be split into 2. That can be a useful thing to do, but there's a couple of caveats. First of all, it's not necessarily a no data movement operation. If you had 10 million rows between 10 and 20, and you said, now split this into 2 partitions with a new boundary point at 15, you might end up moving millions and millions of rows. That's one thing to be aware of. Another thing is, one partition function can actually be applied to multiple tables. So every single table that uses that partition function is going to be impacted if you do a split. Merge is the opposite. Merge says remove a boundary point. Merge, I could get rid of the boundary point at 30, so then everything between 20 and 50 would all be in the same partition. But again, it's not guaranteed to not move any data. It depends on whether the partitions are already populated. If you try to merge two empty partitions, there, of course, is no data movement. If you add a new boundary point, which is less than the lowest value, there won't be any movement. If you add a new boundary point, which is greater than your greatest value, then there won't be any data movement. But there's no guarantee. You have to be careful and do your testing. If data moves, it's a regular data movement operation. SQL Server logs the data movement. It locks the data as it's being moved. There's a lot of resources needed if you do a split or a merge and data actually has to move. And the partition numbers, 1, 2, 3, 4, 5, will change because they're always sequential. If you split something in the middle, what used to be partition 5 now might be partition 6 because the numbers stay sequential. So, I've mentioned most of these points. Many tables could be affected if you use the same partition function over and over. You do need to make sure there is a new file group. If you do a split, you've got one more partition, you need a file group for it. There is an option to alter partition scheme to add the next used file group, which means the next time I do a split, use this new file group. Best practice is to always split empty partitions so that there will be no data movement. For merge, we want to first switch the data out, and then we can do a merge of an empty partition, and if you're careful, get no data movement in that case. So there is a script that will allow you to take the tables I just worked with and try doing split and merge if you actually want to see that happen and see the metadata after you do that. It's a very important thing in certain applications to be able to do, but unlike switch, which is always, always metadata only, split and merge are not they're not guaranteed to be metadata only, so that's why you need to do testing. So I wanted to give you the background here for what partitioning is all about, but in order to really understand it, we had to get into a little bit of SQL Server's storage metadata in general, which is always an important thing to have a solid grasp of if you're organizing your data. If you're responsible for your data storage, being able to take a look at how and where it's stored and how much space it's using, being able to do that is never a wasted skill. So we looked at basic storage. We looked at what partitioning was all about. I spent time showing you the script for switching partitions in a couple of different directions. There's also a few more examples in the scripts to switch from I mentioned the large object. I think there's one more example with some indexes to see how that affects the switching operation. Redefining the partitions is done with the split and merge, and they're very useful commands in some cases, but you need to test and be very careful. So thank you very much for being here. Please make sure and fill in your evaluation for this session and all the sessions so that the conference folks can make sure that this is the best that it can be for you. There's a party tonight, don't forget, and I hope you have a great rest of the show. Thank you very much. Thank you.